The last topic we're going to be looking at is the derivative of an inverse function. So when we're talking about the derivative of an inverse function, you might say, oh man, that's easy. All you do is determine if an inverse exists. Follow the steps and find the inverse. And of course, lastly, and take its derivative. What could be simpler? Well, the problem comes in with this second step right here. Sometimes it's difficult to find that inverse. So what do we do if the inverse can't be found? Well, we're kind of usually stuck. We can do some modeling situations, but for now we just want to look at an example where we actually cannot find the inverse. So let's go ahead and look at an example where we have a function f of x equals 2x to the fifth plus x cubed plus 1. Okay, first step, does an inverse exist? Well, we could look at this graphically, so you could grab Maple and graph this in Maple, but I'm going to go ahead and look at this from the calculus point of view. So the derivative here would be 10x to the fourth plus 3x squared, and since all my powers are even, I know this is going to be positive for all values of x that I can choose. This is monotonic increasing, and if I have monotonic behavior in a function, then this implies an inverse exists. So we know an inverse exists. I guess that's not a question mark. It does exist. Okay, so the second step would usually be to find that inverse. And this is where we're going to run into trouble. The first step in finding an inverse, if you'll recall, is to solve for x as a function of y. And that's where we run into trouble. This means we want x equals stuff over here that's only in terms of y. There could be a constant like a 3 or a 1/2 running around, but there cannot be any x's. I need to isolate x on one side and on the other side have all values of y. So let's go ahead and see if we can do this. Our original function was y equal 2x to the fifth plus x cubed plus 1. And I don't know why that parenthesis was up there. Okay. Can I solve this for x? Can I get this in terms of x equals stuff? No can do. I can't do that. So I know an inverse exists. I just don't know how. I just don't know what that inverse function is. So I cannot take the derivative of it. So because I cannot find the inverse, I cannot take the derivative. And you might say, you know, yay, one less thing to take the derivative of. But actually it's really too bad, because now we're going to have to find other techniques to allow us to find the derivative of an inverse function when we don't know what that function is. So let's go ahead and look at a theorem that talks about the derivative of an inverse function. So here we have a theorem that talks about the derivative of an inverse function. First of all, it says assume that the original function is differentiable and 1-to-1, and we know what 1-to-1 means. That means it passes both the horizontal and the vertical line test. And let g of x represent the inverse of f. Now, if f is a member of both the domain of g and f, then what we can say is the derivative of the inverse evaluated at b is equal to this rational expression. So let's go ahead and look at an example to see what this is talking about. So for this example, let's go ahead and use that same function I was just working with. And let's let f of x equal 2x to the fifth plus x cubed plus 1. And I would like to find the inverse of this function evaluated at -2. Or another way we can represent that is g of -2, because we realize that g actually is representing the inverse function of f. So from the formula that we have up above, we are looking for g prime at -2. This means I want to take the inverse function of f and evaluate it at -2 after I've taken the derivative of that inverse function. So the inverse function of f derivative evaluated at -2. Well, according to this formula, this is equal to 1 over the derivative of my original function evaluated at g of -2. So I need two things to work this problem. First of all, I need f prime of x. I need the derivative of x. And I also need my inverse evaluated at -2. Well, this is the easy part. F prime of x is easy. That's just 10x to the 4th plus 3x squared. We already found that once when we were trying to determine if an inverse existed, and we found out it was monotonic. Now the more difficult part here then is to figure out what is g of -2. G of -2. Well, remember, one of the key factors that we talked about with the domain and the range of inverse functions are the domain and the range swap. So this value right here of -2 is the domain of the inverse. The domain of the inverse becomes the range of my original function. So this becomes the range of my original function. So the domain of the inverse becomes the range of the original function. Also, the range of the inverse becomes the domain of my original function. Or, you can say it the other way, the domain of my original becomes the range of the inverse. So this is what I'm looking for. This is the piece I don't know, and I'm just going to call it A, just for simplicity's sake. So how do I figure out this value of A? I don't know the inverse and I can't figure it out, so I have to work with my original function. My original function was 2x to the 5th plus x cubed plus 1. That was my original function. So f of A is going to be equal to 2a to the 5th plus a cubed plus 1. And I have to set this equal to -2. I have to set it equal to -2 because of this value right here. Well, there's a lot of different ways you can solve for this. You can solve it in Maple, and you can solve it on your calculators. If you solve it in Maple, the only thing you need to do is to input the function. Sorry, that's a different plot from today. And then right-click on the function. Okay, and make sure you put in that equal sign and choose Solve. Okay, and solve numerically, and that's all you do. Okay, and if you go through that process, we get here that A equals -1. So this equals -1. This equals -1. So going back up to my formula then, from right up here, I'm going to go ahead and grab this. Oh, and all sorts of crazy things just happened when I scrolled up. Okay. So coming back up here, I already have some information. Oh, this popped back in, so that was good. So what this is going to look like is 1 over f prime. Now remember, g of -2 from right up here was equal to -1. This means my first derivative evaluated at -1. Well, my first derivative was 10x to the 4th plus 3x squared. So 10 -1 to the 4th plus 3 -1 squared, which is 1/13. This is really cool. That's what this is. Whoop! So I'm not going to try and put a box around that because bad things seem to happen. But what this is saying then is I never even knew what this function was, but I was still able to evaluate the derivative of that function at a particular point. One important takeaway from this is the graph of inverse functions have reciprocal slopes. And you might say, well, wait a minute, I don't think so. But let's go ahead and look back up at our original picture that we had up here that we drew. Way up here. Here we are. Now look at both of these functions. The slope here is 1. The slope here is 1 as well. And of course the reciprocal of 1 is 1. So the graphs of inverse functions do have reciprocal slopes. Now in section 7.3 we'll be actually looking at the inverse function of e to the x type of functions.